So this is my fourth Quidio. First question is the basic question, and it reads, the Gallup poll asked a probability sample of 1,785 adults whether they attended church or synagogue during the past week. Suppose that 40% of the adult population did attend. We would like to know the probability that an SRS of size 1785 would come within plus or minus 3 percentage points of this true value. So part A asks about the mean and the standard deviation of this p-hat, and the mean is just the probability, so that would be 0.40 since they told us that the probability is 40% of the adult population. And then the standard deviation formula you would use for this is p with parentheses 1 minus p divided by n, and that whole thing is going to be taken to the square root. So that's 40.40 since that's the probability. And then 1 minus 0.40 would be 0.60. And then n is 1785, so you take all that together and you get 0.0116. Part B asks to explain why you can use the formula for the standard deviation of p-hat in this setting, aka the rule of thumb number 1. And that rule of thumb is that the population needs to be at least 10 times larger than the sample size. And we can definitely say that there are more than 17,850 adults within the US, so rule of thumb number 1 is appropriate. So we can use that formula of the standard deviation in this equation. Part C asks to make sure that you can use the normal approximation for the distribution of p-hat, which is rule of thumb number 2, and that's just making sure that n times p is greater than 10 and n times q is also greater than 10. So p again is your probability, so you do 1785 times 0.40, and that is 714, so that's obviously greater than 10. And then q is basically the opposite of p, it's just 1 minus p. So that is your 0.60, and that is 1071, which is again greater than 10, so that rule of thumb checks out. So the last part of the basic question asks to find the probability that p-hat takes a value between 0.37 and 0.43, and that is within 3% plus or minus of the true population proportion, so that's where we got those numbers. So you're going to subtract 0.40 from 3.7 and then divide that by the standard deviation, and you get negative 2.586, and then you go to your table A and you find 0.0049, and then you do the same thing with your 0.43, and that comes to 2.586 positive, which comes to 0.9951 in table A. And then you subtract those because you're trying to find in between, and you get 0.9902. So the question was if an SRS size of 1785 will pretty much always give a result of p-hat within 0 or minus 3% of the true population proportion, and I said yes, because if 99% of the data falls within that plus or minus 3%, then we can almost guarantee that your data is going to fall within there. So the advanced question was about researchers who were interested in comparing two methods for estimating tire wear. They used the weight of the tire, and they also used the groove of the tire, and then calculated the difference between those numbers for 16 tires. Part A says to construct and interpret a 95% confidence interval for the mean difference in the estimates from the two methods in the population of tires. So, the confidence interval formula is right there. And to find the mean and the standard deviation, you put in the data of the differences from all 16 of those tires. I put them into L1 and then did arrowed over to calculate, and then one variable statistics, and that's where I got those numbers. And then this, instead of using z-score like we have lately, we're actually using t-score because they give you no population. And with that, you need degrees of freedom. And how to find that is you do n minus 1, so that was 16 minus 1, so that's 15. So you go to table A and you find 15. And so you go to table C and you find 15. And then you're going to go to 0.025 because since it's a 95% confidence interval, we have 5% left over. And that 0.025 column is kind of like 2.5%, which would be like the tails of the bell chart if you wanted to draw that. So you go to that and you get 2.131. So once you get all that, you know that your N is 16 because they told you that there are 16 tires. So you plug all that into the formula and you get a confidence interval of 2.837 to 6.275. So the statement you want to write is, we are 95% confident that most, aka the middle 95%, of data concerning the mean difference between the two methods will be between 2.837 and 6.275. Part B asks, does your interval in Part A give convincing evidence of a difference in the two methods of estimating the wear? Justify your answer. So, I said yes, the interval in Part A gives evidence that the two methods of estimating tire wear is convincing because we are 95% confident that it will fall between about 3 and about 6. And if there wasn't evidence that there was a difference, then it would be 0 because there wouldn't be any difference since the methods would be measuring the same way. But since there is a difference between the measurements, we do have that confidence interval. So yes, there is convincing evidence. So the AP question for this video asks about golf balls and the standards that need to be met for them to be used in professional tournaments. And one of them is that they cannot exceed 291.2 yards distance-wise. So part A asks, if the manufacturer sets the mean distance traveled to be equal to 288 yards, what is the probability that a ball that is randomly selected for testing will travel too far? So too far would be anything over 291.2. So you're going to use the formula x bar minus mu over standard deviation. And so your 291.2 is going to be your x bar, and then your 288 is going to be your mu, and then you're going to divide that by 2.8, and you get 1.147. You get 1.14, and then you go to your table A and find that, and then you're going to get 8.8729. But we're trying to see if it's above 291.2, so you're going to subtract that from 1, which gives you 0.1271 or 12.71%. So, part B asks to assume the mean distance traveled is 288 yards and that 5 balls are independently tested. What is the probability that at least one of the 5 balls will exceed the maximum distance? So, the probability that at least one will exceed, which would be 1 minus the probability that all 5 are less than or equal to. So we already got the probability that one of the balls will pass. So you use that, but you subtract it from 1, and you get 0.8729, and you multiply that 5 times since there's 5 balls, and then you subtract that from 1, and you get 0.4932 or 49.32%. Okay, so part C of the AP question asks, if the manufacturer wants to be 99% certain that a randomly selected ball will not exceed the maximum distance of 291.2 yards, what is the largest mean that can be used in the manufacturing process. So you're still going to use that formula of x bar minus mu over standard deviation equals z. But to be 99% certain, we actually want to find the 98% z-score, because that gives you the actual 99%. And if we went to the 99% z-score, then we would get the middle 99. And we want the original 99. So you go to the 98% z-score, and that is 2.33. So your x bar, again, is 291.2. Standard deviation is 2.8. So you plug those in, and you kind of have to solve it backwards this time, but you end up with 284.676. So that is the largest mean that can be used in this manufacturing process to get the standards that they need to get.